Hello everyone, this is lecture 20 of the subject analog circuits. In this class I am going to discuss about current mirrors. This is the topic of unit 4 of the subject analog circuits. So, in this class I am going to discuss the basic current mirror using BJT, then the basic current mirror using Mosfet and the problems associated with the Mosfet current mirror. Now, starting with the current mirror, as the name suggests, the current is mirrored. It means that whatever input current we give, then that input current that will be equal to output current. Let us say vice versa, the output current will be equal to the input current, the output current it will be the mirror of the input current. That is why it is called current mirror. So, current mirror is a circuit in which the output current it is the mirror of the input current, output current is equal to input current. Basically, this current mirror it is used in biasing and also it is used as a active load. So, this current mirror is not new to you. In unit 1 when I was discussing the biasing in BJT and Mosfet, there was a biasing technique, that is the biasing using constant current source. So, that circuit is biasing using constant current source in BJT and Mosfet both. Let us take the example of Mosfet. So, at the source terminal we connect a current source, this is your plus VCC, this is minus VCC and this is the gate resistance RG and drain resistance RD, this is the current source I. So, this current source it stabilizes the DC operating point, and this current source it is made up of basically the current mirror, that is the one application. Another application of the current mirror we will discuss in upcoming classes when in case of differential amplifier with active load. So, this current mirror it will be used as an active load in differential amplifier, fine, that is the another application. So, basically in case of BJT, so the biasing using constant current source in the BJT, what is the advantage? The advantage is when we use this current source, that is the current mirror in the biasing circuit, then the operating point, then that biasing technique it becomes independent of beta and the temperature. There I had discussed this point, that is the just the application of this current mirror. This current mirror is used to design this current source, fine. Ideally the input resistance it should be 0 and the output resistance should be infinite. Practically the input resistance of the current mirror it should be as low as possible and output resistance it should be as high as possible. In current mirror circuit we used matched transistors. Let us see that what is this matched transistors. So, before that we are going to study different types of current mirrors. The first current mirror which we are going to study in this class, that is the basic current mirror. In short, this current mirror is called CM, current mirrors, right. Then there is some problem associated with the basic current mirror. To remove this problem, there are various current mirrors proposed in the literature. One is your base current compensated current mirror, base current compensated current mirror. Another one is Wilson current mirror, cascade current mirror, and one more current mirror, normally we say it is a current source, that is your Widler current source, Widler current source, this is Widler, right. So, there are other types of current mirror also, but we will be restricted to only these current mirrors. So, starting with the basic current mirror. So, firstly I am going to discuss the basic current mirror using BJT. So, the concept of current mirror is what we do, we take two BJTs and we short the base of both the BJTs Q1 and Q2 and short the emitter of both the Q1 and Q2. It means that the base to emitter voltage for Q1 transistor, it is equal to Q2 transistor. That is the first requirement. Why we are doing so? Because if the base to emitter voltage of Q1 and Q2 are same, it means that the collector current will be same, fine, if both are the mass transistors, and this Q1 and Q2, it should be in active region. Mass transistor means the saturation current, reverse saturation current are same, beta is same, fine, and Q1 and Q2 it should be in active region for BJT, but in MOSFET that should be in saturation, fine, because BJT works as an amplifier in active and MOSFET works as an amplifier in saturation. Now see, this I reference is the input current, I naught is the output current. We can find out the relation between the input current and output current. From here we can see that this is I reference current and let us say this is IC. So, this I reference it will be divided into two parts, one is your base current of Q1 and another one is the base current of Q2, IB1 and IB2. So, we can write I reference is equal to IC plus IB1 plus IB2, and since both are mass transistors, let us say IB1 is equal to IB2, that is equal to IB. So, we can write it as 2 IB, and what is IB? IB is IC by beta, fine. The same thing here, the first equation, just see to it, IC plus 2 IC by beta, take IC common. Now, I naught upon I reference will be IC upon IC into 1 plus 2 by beta, IC will cancel out, then output current upon input current is equal to 1 upon 1 plus 2 by beta. Actually, this IC is your output current, because the collector current of both the transistors are same. One more thing, this Q1 should be diode connected. If the base and the collector of any BJT is shorted, then that act as a diode. So, this Q1 should be diode connected. Why it should be diode connected? Because if it is diode connected, then if there is a change in the input current, then that change will reflect in the base to emitter voltage, and base to emitter voltage of Q1 and Q2 both are same. So, corresponding to change in VB, your output current will change. By doing this, your output current will track the input current. If this Q1 is not diode connected, what will happen? What will happen? If the input current changes, I reference changes, then corresponding to that I reference, VB will not change. If VB will not change, then your output current will not change. It means that if there is a variation in input current, then there will not be any variation in output current, and current mirror means the output current should be equal to input current. If your input current is changing, then accordingly the output current should change. It will only happen if this Q1 is diode connected, otherwise this tracking of input current it is not possible, fine. So, this is the relation between output current and input current of basic current mirror, that is 1 upon 1 plus 2 by beta, and of course, what we want? We want I naught is equal to I reference. So, just see this equation A, let us say this is equation A. So, in which case we will get I naught upon I reference if your beta is equal to infinite. If beta is infinite, then 2 by beta will be 0, then I naught will be equal to I reference. So, obviously practically it is not possible to get beta equal to infinite. So, what we want? The beta should be as large as possible. So, in that case your current transfer ratio it will be 1, current transfer ratio, that is I naught upon I reference, fine. We will move towards the ideal case. The ideal case is the output current is equal to input current, exactly equal to input current. For that the beta should be high. Now, this current repeater is just the extension of the basic current mirror. So, this is your basic current mirror. Now, if we want the same current at the different transistors, what we need to do? For example, Q2, Q3, Q4 transistors, Qn transistor, n number of transistors we can connect, and the base of all the transistors are shorted and emitter of all the transistors are shorted. Then in this case I reference will be equal to I1 equal to I2 equal to I3 equal to I4 equal to In, that is equal to I reference upon 1 plus n plus 1 upon beta. What is capital N? Capital N is the number of that transistor. For example, if you want to calculate the collector current of Q1, then capital N will be 1. Fine. So, this current repeater circuit, it is very much used in multi-stage amplifier, because there are many stages in cascade. So, we need that biasing current, and we simply design a basic current mirror and further just copy that current by using an additional transistors. So, this is called current repeater, because the current is repeating itself. Fine. Next is the basic current mirror using Mosfet. So, in the basic current mirror using Mosfet, just replace those two BJTs with Mosfet. So, the Q1 and Q2 are the Mosfet. Again see, in Q1 and Q2 the gate is shorted and the source is shorted, and Q1 is diode connected. Q1 is diode connected, because the reason is the gate and drain terminal are shorted. If the gate and drain terminal of any Mosfet is shorted, then it is called MOS diode, and it will be always in saturation region. You can verify it. I had already discussed the different region of operations of Mosfet, what are the conditions for linear region, what are the conditions for saturation region for Mosfet in unit 1, right. Now, see, if VGS of Q1 and Q2 are same, it means that the output current will be equal to input current, the drain current will be equal, provided Q1 and Q2 are in saturation, and we know the drain current equation in saturation region, that is 1 by 2 mu n COX W by L VGS minus VT whole square. This is the drain current equation in saturation region. Now, see, Q1 and Q2 are matched transistors. Matched means the mu n COX will be same, W by L will be same, VT will be same, and VGS is of course same, because the gate and source are shorted. Fine. So, if the VGS is same, so you can see that your drain current of Q1, it will be equal to the drain current of Q2. It means that the output current is equal to input current. Now, the question arises that if it is happening so, then why we have shorted the drain and gate terminal of Q1 transistor. So, let us understand it, why we have shorted it. See, consider the case if this is not shorted, if Q1 is not diode connected, then what will happen? So, we will give some bias voltage at the gate of Q1 and Q2, let us say it is a VB. Now, if there is a change in I reference current here, then how this output current I naught will change? How this output current I naught will change? I naught is basically the drain current of Q2. If I reference is changing, then I naught will not change. It means that I naught will not track the input current, output current will not track the input current. So, this is not the current mirror circuit, this is not the current mirror circuit. Current mirror means the output current should track the input current. Here, if the input current is changing, the output current is fixed, it is not changing, it is not current mirror. But what happens if we short the drain and gate terminal? Then in this case, what happens if there is a change in input current, then corresponding to this change, there will be the change in gate to source voltage of Q1 transistor. Since the gate to source voltage of Q1 and Q2 both are same, so if there is a change in VGS, so there will be the change in VGS of Q2 also, of course, and corresponding to this change in VGS of Q2, there will be change in the output current. So, what is happening here? Actually, the current is converted into voltage, further that voltage is converted into current. The current, if the I reference is changing, that change reflects in VGS, current to voltage, and if VGS is changing, then corresponding to this VGS, I naught is changing, voltage to current. So, we can say that this current mirror is the combination of current to voltage and voltage to current. So, for copying action, it is very much important that this Q1 should be diode connected. If it is not diode connected, then the output current will not track the input current, output current will not track the input current. And of course, this Q1 and Q2 transistor, it must be in saturation region, because as I have already discussed the drain current equation for saturation region, right. So, it is mandatory that Q1 and Q2 should be saturation for MOSFET and Q1 and Q2 should be inactive for BJT, fine. Now, here we can calculate the relation between I naught and I reference. What is I reference? I reference is the drain current of Q1 transistor. We know that the gate current of MOSFET is 0. So, we can write it as 1 by 2 mu n Cx W by L Vgs minus Vt whole square. Let us say the W by L ratio, that is aspect ratio of Q1 transistor, is W by L 1. Now, what is your I naught? I naught is 1 by 2 mu n Cx W by L 2 into Vgs minus Vt whole square. W by L 2 is the aspect ratio of the Q2 transistor. Vgs for both the transistors are same. So, what will be the value of I naught upon I reference, output current upon input current? It will be W by L of Q2 upon W by L of Q1. So, in which case we will get I naught upon I reference? We will get output current equal to input current only when the W by L ratio of both the transistors are same. Even we can amplify the current also. If we put the W by L ratio of Q2 2 times of Q1, then we will get double current at the output. So, we can use this current mirror as a current amplifier also. To use as a current mirror, what we need to do? The W by L ratio of Q1 and Q2, it should be same. If we want more current at the output, you can increase the W by L ratio of Q2 transistor. The same thing happens in BJT also. If we increase the emitter base junction area of BJT of Q2 transistor, there also we can increase the current, the output current, fine. Here we increase the W by L ratio, that is aspect ratio, W is the width of the channel, L is the length of the channel, fine. Next is the problems associated in MOSFET current mirror. So, there are 3 major problems. One is channel length modulation. Now, see what the equation which we have used in saturation is 1 by 2 mu n Cx W by L into Vgs minus Vt whole square. But here we have neglected the channel length modulation, but we know that practically this channel length modulation effect comes into picture, that is also called early effect. When we take this channel length modulation into account, so we multiply with one more term, that is 1 plus lambda Vds. Similarly, we can write the output current equation, the same thing, 1 plus lambda Vds. So, it means that the Vds of the both the transistors Q1 and Q2 should be same. If it is different, let us say for Q1 transistor the Vds is Vds1 and for Q2 transistor it is Vds2, then what will be the relation between output current and input current? If W by L ratio of both the transistors Q1 and Q2 are same, then what the equation we will get? It will be 1 plus lambda Vds2 upon 1 plus lambda Vds1, where lambda is the channel length modulation parameter. So, what is happening here? See, practically this channel length modulation effect will be there, means lambda will be there. It means that the drain to source voltage of Q1 and Q2, it should also be same. If it is not same, then there will be the variation in the output current. It will not be the same as input current, fine. So, in the circuit of the basic current mirror using MOSFET, we have seen only VGS, we have talked about only VGS, but VDS, drain to source, it also plays a role because of this channel length modulation effect. So, it is very important the VDS of both the transistors should be same. If it is same, then you can see that both the factor numerator and denominator will cancel out, then again we will get I naught upon I reference, fine. So, this is one problem in MOSFET current mirror, channel length modulation, obviously that comes into picture. To combat this effect, there are other current mirrors like cascode current mirror, in which this channel length modulation effect we can minimize it, fine. But in the basic current mirror, this is the issue. Now, the next problem is threshold offset between two transistors. What is this threshold offset? since we know the drain current equation 1 by 2 mu n Cux W by L VGS minus VT whole square, this is the drain current equation of the MOSFET in saturation. Now, see, threshold offset means, since I have already mentioned both the Q1 and Q2 transistors in current mirror, it should be matched. Matched means the threshold voltage of both the transistor, it should also be same, fine. But practically what happens, VT, this threshold voltage may vary slightly, it may vary slightly, right. So, in this case what will happen, the output current equation, it is 1 by 2 mu n Cx W by L VGS minus VT whole square. Now, if we want I naught equal to I reference, then W by L ratio should be same, but if your threshold voltage, it is not same for both the transistors, although matched transistor means threshold voltage will be same, but practically in the fabrication, when the MOSFET is fabricated, it may happen that there may be slight difference in the threshold voltage value of the Q1 and Q2. Due to that, there will be error between the input current and output current. That is the another issue. The third one is imperfect geometrical matching. What is imperfect geometrical matching? See, we want I naught upon I reference, means the W by L should be same for Q1 and Q2, but in the fabrication, due to various fabrication processes which happens in fabrication laboratory like etching, photolithography, diffusion, oxidation, it may happen that W by L, it may not exactly same for Q1 and Q2. If there is a slight variation in W by L in the fabrication, then you can see that there will be an error between the input current and output current. So, these are the some issues with the basic current mirror using MOSFET. See, in threshold, in the second issue, that is the threshold offset between two transistors. To combat this issue, what we can do, if we increase the value of VGS, right, then this variation in VT, it will be slightly less dominant, but increasing VGS means higher current. That is one solution. In imperfect geometrical matching, what can we do? We can increase the W by L ratio. If the W by L ratio, it is very larger, it is very large in comparison with that typical variations during fabrication, then this effect can be minimized. But again, if W by L is more, current will be more, power consumption will be more, fine. See, these are the practical issues which happens at the fabrication, in the fabrication laboratory, but this channel length modulation effect, we can minimize it using some advanced current mirror available in the literature. Next one is the current repeater using MOSFET. See, I have already discussed the current repeater using BJT. Similarly, we can design the circuit for current repeater using MOSFET. Just what we need to do, this is your input current I reference, and here two MOSFETs we have connected, and the gate and source of this Q1 and Q2 transistors are at the same potential, and this Q1 is the diode connected. This is your output current I naught. Similarly, if we connect another transistor Q3, and if the gate terminal of Q1 and Q2 is shorted to the gate terminal of Q3 and the source terminal is shorted to the source terminal of Q1 and Q2. So, the point is that if the gate and source potential of Q3 is again same as Q1 and Q2, then we will get I3 that is equal to I naught, provided the W by L ratio of Q1, Q2, Q3, it should be same. So, we can extend this Q1, Q2, Q3 up to Qn. So, we can repeat this I reference current multiple times. Just what we need to do, if we are adding some additional transistors, then we need to make sure that the gate and source of those additional transistors Q3, Q4, Q5, Q6, Qn, it should be same, it should be shorted to the gate and source of Q1 and Q2. And one more thing, this Q1 should be diode connected, and the second thing, all the MOSFETs, it should be in saturation region. Again, it can be used in multi-stage amplifier, because there are multiple stages, we need some bias current at each stage. So, we can use this current mirror there, fine. So, it is very much useful in IC designing, especially this current repeater using MOSFET. And in today's era, since in IC only MOSFETs are fabricated, so this current repeater using MOSFET, it is very much used, fine. So, in this class I have discussed about the current mirror. What is current mirror? Ideally the input resistance of the current mirror should be 0 and the output resistance should be infinite in order to avoid the signal loss, fine. Then I have discussed the basic current mirror using BJT, basic current mirror using MOSFET, then the problems associated with the basic current mirror using MOSFET, then after that current repeater using BJT and MOSFET. This is the reference. Thank you.